maybe natural mass violation persist. That would be super weird. And if it's true, I really want to understand it. But yes, I want to try to see if we can validate that argument because it seems too good to be true. So what I'm thinking is, so the basic issue is the following: these deformations that are crucial to the story. They have an abstract definition as equivalent operators, but that definition is totally useless. It's like very hard to use. So it's very nice if you have a way to think about them as normal local operators built out of fields, because then you can do factor better. Yeah. But that I only know how to do with the Boson-based. And then if you try, well, I don't. Basically, I don't.
I think there also
yes, absolutely, absolutely.
In the one function.
Absolutely, it's all there in the lattice, but they are very simple in the lattice. If you want to write them down in the continuum using the fermionic version,
it's on the lattice.
Yes, you could say it that way. I mean, another way of saying that in the Euclidean lattice is it's
thinking about something.
Yeah. Yeah, in Euclidean lattice, you just prescribe. But if you try to figure out what this means in the continuum, at least, I don't know. I do know how to do this. So in the bosonized variables, the is that flux insertion, which is what this thing is. It's a fractional flux insertion. It maps to something very simple in terms of the dual scale. And that simple looking thing does not have a nice map to the fermionic theory. It doesn't quite map to a standard local operator. It maps to some weird operator with lost string. I have to defer to you. I haven't thought about the Hamiltonian relation.
Yeah, you want something that's essentially if I try it.
Yeah. That sounds right.
Yeah, I guess in continuous project, it makes sense of this because on the left, they were
yeah,
continues on something because you just see
but yes.
On the left too, you couldn't figure out.
But you could do hopping calculations. So my idea is basically very trivial. You could choose to bosonize mass putative to massless charge on scalar, and keep the other one. And then what you have is basically axial knowledge of tendencies and functions. But the would-be topological operators, they're not going to be exactly topological, they're just built out of the bosonized stuff in each field. And so in principle, you should just be able to go on. Yeah, like basically, like you want to ask, like, what kind of axiom master does loops of the card work? You should get totally answerable question. That's how this is. I understand. We could better understand it because what can you do with them? Let's see if you get with that. We have some idea from there.
あ、ごめんなさい。携帯来なかった。ちょっと。
Well, sorry to miss your talk. It's nice to see you.
指がついたんですけど、ちょっと。See you in 3 months.
See you.
I think we can start. So we have Muneto Nitta talking about how Baryons appears in the low energy QCD.
Thank you very much. Especially, I'd like to thank the organizer who invited me. So I will talk about new phase in QCD. So I have to apologize that my talk is not so related to supersymmetry. I will mention about supersymmetry in the video. So in low energy limit, QCD is described by chiral Lagrangian, where a chiral symmetry is spontaneously broken. So only pion degrees of freedom are relevant. So the question is that in chiral Lagrangian, how baryon can be described? So of course, for instance, one of direction is scan model. But the scan model, you need a higher derivative than scan term. So it may depend on model. And along this, about this question, actually, in the case of, in the presence of finite chemical potential with magnetic field, Son and Stefanov gave some answer. In phase diagram of chemical potential and magnetic field, in certain region, there appear sign chiral soliton lattice, which is actually sign Gordon lattice. And this each of these soliton carries baryon number. And in my talk, I will explain that I will find that within this chiral soliton lattice, actually in the region with a chemical potential which is greater than some critical value, there appears Skyrmion inside a soliton, looking like this. And I will call this domain of Skyrmion lattice or domain of Skyrmion crystal. And in this case, both soliton and Skyrmion carry a baryon number. So this is a ground state, not the vacuum. In the this is a ground state. That means the minimum energy state. So anyway, in certain region, this appears. So I will show this result in chiral perturbation theory at the leading order with OP squared. without any higher derivative scam term. So our result is model independent. And another thing that at some critical chemical potential, previously Browner Yamamoto found that this chiral soliton lattice becomes unstable. But the final state was not known before. So our finding of this critical chemical potential coincide with their point of instability of chiral soliton lattice, in which charged pion condensate. So actually, this soliton lattice is made of neutral pion. Chiral charged pion is not excited. However, at this point,
What's the difference? Yellow and then blue. Is there a difference between these two walls?
this
On the left.
no, this is no difference. Yeah, just for same domain of sign lattice.
I'm not familiar with this. What is the spatial structure of this lattice? So there is magnetic field and where is the
Magnetic
lattice?
field is one direction.
Okay.
Then along this direction, this lattice, chiral soliton lattice. So soliton has 2 + 1
I see.
individual particles. It's a ground state.
But this is the real magnetic field.
Real magnetic field.
So you include electromagnetism.
Yes.
Couple pions to the photons, right?
Yes.
Okay.
However, at the leading order, this magnetic field is just external field, background field.
Okay.
So anyway, this part is relevant inside neutron star or heavy ion collision. So another interesting point is that this critical mu b chemical potential can be regarded as nuclear saturation density, above which nucleon can be created. So what we found is that such nucleon saturation density can be written as in terms of pion information, pion decay constant and pion mass.
Another here.
Okay,
This one.
okay, thanks. So since this above this nucleon is created, however, this nucleon kind of nucleon mass can be written only in terms of pion. This is a kind of surprising result, I think. So let's go to the detail. So this is a chiral Lagrangian of pion degree of freedom coupled with magnetic field. And here A mu B is baryon gauge field that is taken to be mu B 0. And this is actually Betzumino term for with at the finite chemical potential, and which is written like this way. And as I said, we have one magnetic field in one direction. And in their study, they ignored charged pion. They considered only neutral pion. And this term, J mu B, this term, A mu B, J mu B, gives can be written in this way. So J mu 0 component is a baryon number density. And if in the background of magnetic field, this part gives this part can be written like this way. And here mu b is chemical potential for finite density, and B is magnetic field. And this is the pion total derivative term of neutral pion. So this is a topological term which doesn't affect equation motion. However, this count soliton number, so it contributes to the energy, although it doesn't modify equation. Then by solving in this setup, okay, so this is a reduced Lagrangian with setting charge of Baryon to be 0. Then, as I said, this term becomes topological. And this is nothing but the Sine-Gordon model with a topological term. That is called the chiral Sine-Gordon model in condensed matter property. And in fact, in chiral magnet in condensed matter system can be described with the same same Lagrange.
You mean Delashinsky-Marie
Yes.
instead of chemical potential?
Yes, instead of chemical potential, Jelinsky-Marie interaction gives the same, same term. And by standard Bogomolny completion, we can construct anyway, for instance, single Sine-Gordon soliton. And this energy gives usual domain or Sine-Gordon potential term plus topological term coming from here. And in total, this can become negative. So Sine-Gordon soliton can have negative energy. So it can be created. So uniform state is not a ground state. And Sine-Gordon soliton should be created because it has negative energy because of this basis term. So Sine-Gordon soliton is created in the ground state, but two Sine-Gordon soliton feel repulsion, so that you cannot create an infinite number of soliton. Then ground state becomes this soliton lattice.
Magnetic field is constant, or
Magnetic field is constant in this.
so it's a total derivative.
Yeah, that's total derivative.
Total derivative. I mean, you would think that total derivative Lagrangian does not contribute.
No, for
It doesn't contribute to equation of motion, but it contributes to energy. And it counts soliton number.
topological, domain wall topological.
No, then it boundary term, so right.
It's boundary term, so equation of motion is not modified. However, it contributes to the energy. It counts soliton number. So it can, important is this can contribute to negatively to the energy.
Yeah, no, but then it should be kind of analog of theta, because then there could be a certain kind of periodicity in V.
Yeah, it's analogous to theta term, but it's a kind of pure imaginary, theta term. So this is the actual soliton solution. In this case, of course, chiral soliton lattice can be explained analytically because it's analytically solvable model. But anyway, that is their case. In our case, we include charged Baryon degree of freedom. And this first term, which is neglected in previous work, it plays important role. Because you see this term is the same term with Skyrmion number. So due to this term, which can be presented for non-zero charge Baryon, then we also consider full 3D configuration. Then we found that this domain of Skyrmion, the true ground state, not a Sine-Gordon lattice, in certain parameter region. That is our finding. Then one comment, I have two comments on supersymmetry. In case of lower dimensional version, actually Misha considered similar configuration. That is D equal 2 plus 1 domain O. And the vortex, this is a semi-local vortex, not it's like a baby Skyrmion. If this is absorbed, it splits into two kinks. This is the case of n equal to 1 supersymmetry. Also, I was informed that from Ali that Ali and Misha also considered Baryons on domain wall in supersymmetric QCD. So let's go to the derivation. So first, I will consider single sign Gordon solidon. Then this is a single sign Gordon solidon with neutral pion degree of freedom. But more general solution can be written this way. Actually, it has S2 moduli or corrective coordinate. Here, this is embedded into full SU2 group. Then here phi is actually CP1 moduli. That is a homogeneous coordinate of CP1. And U is just a single solution. So this the most general solution is actually non-abelian cycle solidon that carries S2 moduli. Similar non-abelian solidon can exist in the case of eta solidon lattice under rotation. Instead of magnetic field, if we consider rotation, we also can have similar configuration. Then let me explain that moduli more intuitively. This is S3, full target space. Then we start from C minus infinity to infinity at the North Pole. Then single sign Gordon solidon is something like this, which has this greater, which is expressed by this greater sample. And this can carry S2 moduli because you have to choose the point on the equator, which is S2. You have degree of freedom to choose which point of equator you will pass through. Then this has so that this has S2 moduli. One comment is that Misha and Arkady considered such a domain wall with S2 moduli in different settings. The next step is to construct effective theory domain of the domain wall world volume by using a modular approximation or Manton's approximation, for which one promote moduli to field on the world volume. In this case, moduli is a translational moduli and orientational moduli of CP1. They integrate out over codimension X3. Then we get the domain wall effective theory. This method is well defined and established, for instance, to construct monopole modular space or Instanton modular space. We apply this to this domain wall. So then this is the result of effective action. Effective action contains these three pieces. First two are just constant, expressing domain rotation and topological term for domain wall. Then these are constant. Then this normal term is actually nothing but CPO model, but it's gauged. This is gauged CPO model. Gauged by background gauge field, actually. Then this Bessel term consists of these two terms. The first term is actually nothing but a topological term for 2D Skyrmion or baby Skyrmion, counting characterizing pi 2s2. The second term is a kind of a tricky term that I will explain later. here N is 3 real scalar field, L1, N2, N3, describing the model in terms of O3 as a O3 sigma. So we use both phi over L degree of freedom.
And your phi, does it describe only pi naught or all three pi's? Pi
Yeah,
plus and pi minus don't appear so far.
actually, phi, wait a moment. If phi is 1, 0, it okay, it describes the pi, charged pi of degree of freedom. If we the original wait a moment. That phi describe this S2 moduli.
Okay,
If phi is trivial, like 1, 0, then you have only neutral pi. So this red circle is neutral pi, pi 3. If you turn on phi, you turn on charged pi.
okay.
So the previous study correspond to phi equal 1, 0 without the charged pi. Here we consider charged pi. Okay, then interesting is that this kind of topological term appears in Lagrange. So it's like a pure imaginary theta term. The important is that this contributes to the energy, not like a usual theta. One remark is that we are considering chiral perturbation theory at the leading order. This must be square. So leading order. So gauge field kinetic term is a higher order. So gauge field is non-dynamical in our setting. So this is a Skyrmion, AB Skyrmion configuration. So using phi over n degree of freedom in the boundary is North Pole. Then in the middle, on the center, it corresponds to the South Pole of S sphere. So let's consider explicit baby Skyrmion or ramp solution. This is a Hamiltonian. As I said, there appears a topological term with real coefficient. So the first term is usual O3 sigma term. So you can perform usual Bogomolny completion. But as I said, here there appear a topological term with pure imaginary. With real coefficient. The Bogomolny equation is same with usual Beryons-Polyakov case. Here K is the number of ramp number counting pi to S2. If you look then, if you look at these two terms, here K is absolute value of there appear here is absolute value of K, but here you have only bare K. So this combination of term can become negative. If this is negative, you create a Skyrmion in the ground state. However, this third term plays some non-trivial constraint that I will explain. So this is a ramp solution. Explicit ramp solution. That is actually same with usual Beryons-Polyakov ramp. Then, if you calculate the Baryons number of 3 plus 1 dimension, this Baryons number NB is actually 2K. So one ramp corresponds to 2 Baryons in this case. So although we have pi 2s2 and pi 3s3 correspondence, this is 1 to 2 correspondence. This is not only the not the end of story. although you have several moduli parameter here, we have some constraint, as I explained now. First interesting point is that this ramp is actually nothing but a superconducting ring, because on the boundary and on the middle center, you have only neutral pion. You don't have a charged pion at all. However, there appear charged pion around this ring, this red circle. So this point, this is a superconducting ring. So as is well known for the superconducting ring, you have a quantization condition of flux. So if you calculate this flux, this must be related to actually ramp number. So then this SD is the area of this interior of this circle. So actually, this shows that this SD is a surface, the B is a magnetic field. So area of this area is quantized to be integer. So Skyrmion is now this shape, and its size is quantized to be integer. That is one interesting point. So this is a single soliton, the example of single soliton. In the case of single soliton, for instance, N3 becomes 0 at where omega equal B0. That is on this red circle. So this in this case, this area quantization gives you this quantization of size module. So B0 absolute value of B0 represents this size. So this size is quantized to be determined by magnetic field. So this is the actual solution. We have domain wall, then we have single soliton, single Skyrmion. Although it's single, but in terms of baryon number, it carries 2 baryons. So this looks like a macaron or dorayaki. That is a famous Japanese sweet. Both are sweets. So we call this macaron or dorayaki solid. Then this is the K equal 2. In this case, you can separate. This is 2 soliton top on each other. Then this can be separated. However, you have to preserve area of during this separation. This is a BPS, so you can separate it freely. However, you have to preserve area.
Why is it BPS?
Why BPS? This is satisfied BPS bound.
No, but I mean, in real life, it's not going to be.
Hmm?
In real life, probably it's either attractive or repulsive.
No, BPS.
In QC,
Yes,
no, cannot be that because there is no interaction.
there is no interaction in this case. This is on inside the domain. Inside the domain of Skyrmion is BPS. That is our finding.
Sorry, why?
Why?
The topological charge enters the superconductor.
Yeah, but this module that you called next slide, the next slide, there are this 2K plus 1 moduli.
Yeah, there is.
They are different probably in real life.
Huh?
They are not there in real life.
There is.
They must
We
be
found
different.
this solution.
No.
On-
It's because
on
we
the way.
considered only 2 derivatives. At the 4th derivative, there will be different.
No, we don't have Skyrmion. We don't have 4 derivative.
But there is in real life.
We are considering in the reading order. At least in this reading order.
Yes, the
Yeah.
order they are present.
Yeah, leading order of chiral
But in real life, it's either attractive or repulsive. So one needs to know.
Yeah, if we consider higher derivative order, they will, I think they will repel. Yeah. In this leading order of chiral partition, they are repelled. Yeah. Oh, sorry, maybe, wait, I'm exhausting. So this is the domain of energy. However, there appears one moduli here. This is a very non-trivial. This gives non-trivial concept. For k equal 1, we in different way to k equal 1 and k equal greater than 1. In case of k equal 1, some miracle cancellation occurs between these two terms because of this quantization condition. So for k equal 1, somehow domain of Skyrmion has always positive energy. So single Skyrmion cannot be created on the domain. It can be, but it's an excited state, not the ground state. For k greater than 2, equal or greater than 2, this actually gives a constraint on this modular, bk minus 1. This should become 0 because of positiveness. This is a further constraint, second constraint on the modular. Then in this case, this term can become 0. This term can become 0. So because in that case, when baryon chemical potential is greater than this value, then this term becomes 0. So soliton is created in the ground state. Okay, I'm finished. This is summary. We have a new phase in the plane of new phase of which in the plane of baryon chemical potential or magnetic field. Here we have a domain of scan. Thank you for the attention.
This model that you mentioned, there is a problem with the geodesic incompleteness.
You mean the modular?
Yes. How do you deal with that problem?
You mean the lamp modular?
They are geodesically incomplete.
Right. For small lamp singularity.
This is a big problem.
But however, as I said, lamp size is quantized. It cannot become 0. It's quantized. So these are not okay. So size modular is not a modular. Size modular is fixed. So you don't have such a singularity.
How did you fix it?
By because this is superconducting ring.
You have a dynamical condition,
Dynamical, or it's a kind of so-called. So this area is quantized by because it's a superconducting ring. So it cannot become 0.
We need to move on. Thank you very much. Good. So next we have Peter talking about supersymmetric gauge theories and offers.
Thank you very much. I'm really glad to come back to Minneapolis, the place where I did my PhD from Arkadiusz, my advisor. it's like, in a sense, you can think of Minneapolis as one of the capitals of supersymmetry. Some imaginary superland. So the kind of, I was a bit surprised that I was kind of expecting more talks to be of philosophical nature because kind of it's the 50th anniversary. When I was preparing the talk, I looked at some history. So, so here I took this first for references from my PhD thesis, right? So I'm gonna names all the heroes of supersymmetry. So I think now sort of to avoid very confused confusion, we say that these 8 gentlemen, they kind of pioneered the supersymmetry, right? So Wolfgang Lichtmann, Volker Pakolov, Nitta, Schwartz, and Weston Mina. So probably know that the first paper is actually very remarkable. Like it has 1 citation to a textbook, right? So it kind of shows you how significant the discovery is. The fewer citations you make, the more important. But of course, it doesn't mean that you should not cite your friends, right? Anyhow, so so here's Arkady again. So again, one more advertisement of my thesis. So in the introduction, I wrote this paragraph. So that was in summer 2012, right? And it says here, well, let us mention, however, that it's the status of supersymmetry as a branch of theoretical physics may soon be completely changed from after the new data of SUSY from LHC will come in. So 5 and 6 are references to talks by Incandela and Sanyotti, right? So so there's this 2 AM seminar at CERN that we'll listen online, right? And then so that was just after the Higgs was discovered. And here it says, at the present day, summer 2012, the perspectives of finding SUSY at LHC were not very optimistic. And 7 is just one of the data analysis. In the worst case scenario, when the SUSY will be found not to be present, at least in the form we think about it, phenomenological studies in this direction will be virtually over, and only abstract and formal aspects of supersymmetry will remain in the front line of physics. So that's what my kind of taken 10 years ago, and that is not quite where it all goes, but it's interesting like to meet 50 years from now, right, and see what actually is going to happen, right? So, so in sense, yes, LHC says sorry, folks, but of course it doesn't mean that we should stop working on supersymmetric theories, right? So just some of the key highlights. So there are many. I haven't been here on the first talk, the first day, but probably people mentioned this anyhow. So it helps us to solve theories of strong coupling, right? So then SUSY provides a plethora of exact computations. This is SVZ, yes, Glina condensate, separate Witten. It's very important for string theory. So it was funny, I was attending a colloquium with Aspen and by an experimental physicist from CERN. I forgot her name, but then she said, the talk was about supersymmetry at LHC, exactly kind of what we used. And then her first motivation was, why do we use supersymmetry? And she said, supersymmetry is important for string theory. And it was, I thought that was really cool, like experimental physicists, but really, but I think she adjusted the talk for string theory audience, but that's not anyways. And the last point I want to mention is that, well, the supersymmetry provides us with powerful approach to solve mathematics. So my colleague at Rutgers, Greg Moore, coined this term, sort of physical mathematics is a kind of subset of mathematical physics, which kind of allows you this feedback backwards, right? So from physics to math. So use physics intuition, supersymmetry, string theory to actually prove theorems. And that's partly what I'm working on right now with my math colleagues. So, okay, so let's start somewhere, and then we'll see many familiar pictures and terms from today. So essentially what I'm going to do in the rest of the talk, I'm just going to give you one example, the supersymmetric QCD in 3 dimensions, botanical for supersymmetry, and we'll see what kind of geometric structures we can extract from there just by studying this theory and cyber duality. And this is where this mysterious term Oper will come in. Right, so let's go to type to be string theory. There's this famous handwritten picture, which we'll know and love, and then you can use this to engineer gauge theories with n equals 4 supersymmetry. So they live on this horizontal D3 branes. So here's the brane construction. And then the number of D5 branes between and S5 branes, which are those vertical domain walls, it's kind of serotonin branes, gives us the ranks of the gauge groups, and then the number of D3 branes, the number of the gauge ranks of the gauge groups, and then framings, they are defined by the number of D5 branes. And then sort of the reason why I can get gauge theory is because if you look at fundamental strings, which are and which end on different kinds of branes, it gives you different types of matter content, right? So you have well, gauge group is product of all those guys, right? And there's a flavor group, product of those numbers in the box, and then there's also bi-fundamental matter, which comes from strings that look like this. Okay. And then you can also do symplectic, orthogonal, if you add some orientifold planes. Okay, now this theory has two, notably, this kind of theories have two branches that kind of have intersected the tip, like two cones, which sort of have a common tip, but all fields are zero. And then you can either go into the Higgs branch when the hypermultiplet gets value, or in the Coulomb branch where the vector multiplet gets a value. Right. So let's talk about Higgs branch first. So it's parameterized by webs of hypers. And then essentially its description is completely geometric now. So there's a Kajima quiver variety. So we look at space of all representations of the quiver. So essentially these are just matrices. Like they're parameterized by webs of squark, like Q tilde, and they're complex conjugate, right? So it can become groups of 4, and that's why sometimes people measure those dimensions in quaternionic units, right? So kind of the smallest dimension is 4 real or 2 complex or 1 quaternionian. So you compute this moment map from, and then you have this kind of you double all the space of representations, have a potential bundle into the dual to the Lie algebra of the gauge group. And then the quiver variety is simply it's this simplex, hypersymplectic motion, right? It's a Hamiltonian reduction of the pre-image of 0 under the moment map that has interesting geometric stories. Like next week, I'm going to a conference at Stony Brook where like the whole conference will be about how to understand this properly. Right. So for example, this SPCD that I mentioned have UK SPCD with M quarks, like quarks. So the corresponding Higgs branch is the cotangent bundle to Grassmannian of K planes and Cn, right? And it's classical, does not receive any quantum branches. Unlike the Coulomb branch, which does, but I'm not going to be talking about it too much, I'm just going to mention. So classically, it's in some cylinders, so it's parameterized by webs of vector multiplet, and then sort of you can n equals 4 vector has kind of 2 n equals 2 parts, right? And then the n equals 2 vector has this, you can dualize it to what is called linear multiplet. So it's a familiar story in 3 dimensions. Photon is dual to a scalar, right? And you can dualize the whole multiplet. And then you couple it with the sort of the other scalar. You write it like this, it's called monopole operator, and it's sort of charged under this logical U1 symmetry. It does not appear in Lagrangian, but it's there in the Coulomb branch, and then n equals. Yeah, and then there's also one more complex scalar, and you can sort of look at the gauge invariant combinations of it just by looking at those break by k. So altogether, we have kind of a classical branch, which is this Weyl group quotient of this cylinder. So R3 cross S1 to the power of the rank mod Weyl, right? And but it receives a lot of quantum corrections. So this it's not going to stay like this after you have included this. So this whole cylinder will be pinched at some points. There will be some branches coming in, and now we have a very powerful tool, also described by Nakajima, same mathematician, and two other collaborators. It's called BFN, and there's a critical construction of Coulomb branches in terms of applying Grassmannian. Okay, and then there's a. I'm just going to mention it in passing. There's a 3D mirror symmetry that changes the branches. Now we want to do introduce a deformation. So it's n equals 2 deformation. So n equals 4 has a large R symmetry. SU2 Coulomb cross SU2 Higgs. Essentially, we're going to break it down to U1, the diagonal, the U1R, with the acts with a sort of cartan from here plus the cartan from there, and sort of the orthogonal combination will be lifted. So we'll turn on the mass for it, call it epsilon. This is supposed to star deformation. Then we turn on Fi parameters and masses for the Higgs and the Coulomb branch. And in addition, we can simplify it on the circle, right? So that will allow us to complexify all the fugacities that we have in question. So in a sense, all variables I'm going to be writing in the rest of the talk will be fixed values and non-zero complex numbers. So it's like exponential to something like that. So there's a holonomy of the background Wilson line for each of those parameters, which will allow us to make complex. Okay, and then so this is so-called n equals 2 star 3D theory on R2 process 1. Again, this is the all the data. So we have complexified Fourier-Leopold parameter Z, and then complexified real masses A1 and A2. Right, so it's a SQCD with n quarks, UK, or geometrically it's this Nakajima Quill variety for just the star of Rosmanian in KN. And then now, because everything is massive, I can just integrate out all the fields. There's the exact one loop population. And then the minima of the effective twisted effective superpotential gives us these equations, which are also known in integrable systems literature. They're called XXZ Baryons equations for SL2 spin chains. So when you have a spin chain with periodic boundary conditions, the Z is related to the eigenvalue of the twist matrix, which you use to make a periodic condition, and A is a so-called anisotropies of the spin interaction. So here, some spins are closer to each other than the others, and then for those, the interaction will be strong.
So I think UK SQCD then
So the rank of this thing is related to the rank of the quiver itself. So K appears as the number of excitations here.
if you do n equals to star, don't you get an adjoint?
Yeah, this comes from that joint.
The UK supersymmetric and points.
But it's, in this territory, it also has that joint. So the not joint and the superpotential. Right. So there is an adjoint, of course, yeah.
Usually people draw a circle.
So it's so-called periodic notations. Usually when people draw like this, it's equivalent to drawing here in hypercalar, so we just do this. Other questions? Okay, now the hero of ours, so Richard Feynman. So this is probably seen it from Caltech archives. This is last Feynman's board, right? So it's got a lot of kind of philosophical things on it. For example, like here, what I cannot create, I do not understand, or know how to solve every problem that have been solved. Right? So, but what I'm kind of curious here about is that in the to learn box, you put base and ask problems, and then he was known to say here, I got really fascinated by these 1+1 dimensional models that are solved by the beta and that's, and how mysteriously they jump at you and work, and you don't know why. And I'm trying to understand this better. So in a sense, kind of now we certainly understand a lot about this, but we want to understand even more at some sort of deeper level, geometrical or precipitation theoretical or physical. So that's kind of in the very much in the spirit of what Feynman was doing. Also, other thing I like here is that he crossed out Kondo problem. So like, Richard Feynman understood Kondo problem. Like, good for you, Richard Feynman. For you. Okay. Yeah, as you can see, I can try to find pictures of as young as people as young as possible.
What is the fourth item in this list?
Huh?
I can't read the fourth, but something temperature.
Accel something.
Accelerate. So you mean the Rindler space?
Probably, yes.
Is that
Yeah. And the last one's nonlinear.
so, yeah, Vardeen temperature.
It's probably like the Navier stocks and all this problems. Okay, so now let me show something, a new approach on things that you already know. So, Sarah and other speakers, they mentioned there's this cyber-like duality for those series. Essentially, these are two different ultraviolet descriptions of the same IR physics. What's called the same IR fixed point. So if you have SQCD, UK SQCD with n flavors, it has the same, it flows to the same point, IR fixed point as UN minus K with n flavors, right? And those kind of relations are known as Sudbury-like dualities, essentially like because they're no missing, right? Sort of. And then sort of mathematicians look at about this way. So we have kind of there's a vector bundle V and W. So V, so W is kind of a trivial bundle, and V with some tautological bundle of rank K, right? And then there is this exact sequence, basically we can replace vector bundle with rank K with vector bundle of rank N minus K. Okay, and now let's try to write this down in more concrete terms, right? So we introduce this polynomial Q. First was by Baxter. So just polynomial with the roots. This Si are the beta roots from the beta equation. So they are valves of the vector multiplet, right? In the QCD. So there's a polynomial Q for UK theory, and there's an analogous polynomial Q tilde for the dual, for the Seiberg dual. And now there's an interesting relationship that you can write this quadratic formula for Q and Q tilde, and it's equivalent on the nose to those beta equations, right? So the way to see this is the following. So let's evaluate U at its root, at its 0, right? So then this thing disappears, and we have Q tilde of SI times Q of SI is equal to this. And then you make a Q shift, right? So we shift by Q. Q here is the no, it's not that, is the exponentiated to star mass, right? So of the theory. And then you do sort of evaluate the roots of Q tilde at the shifted root. And then you get the other term will vanish, right? So, and then you can divide one by the other, and you will see that the beta equations will be reproduced. See the equations.
Sorry, can I ask something? So these descriptions are like, I think it makes sense only if you are lifting the Coulomb branch, but it's because you are turning on all the massive deformations. So this is an actual dual. I mean, this is not generic. I mean, the infrared dual is this Seiberg dual only at this level.
Yeah, that's right. So like the actual impulse theories have for the same IR point, but this of course they don't flow anywhere, right? So
no, but I mean, I'm asking if you have, since you are discussing beta vacua, so you are doing isolated vacua, you need to know all the mass deformation, including RFI, so you lift the Coulomb.
absolutely. So we need to.
Then it's correct.
Yeah. So we deform both branches and we lift both branches. Okay. So now let's. Essentially, the idea of Oper comes from this perspective, by combining two duality frames at the same time, right? So let's write the vector in two-dimensional vector with components exactly just Baxter polynomials. Again, so Q has roots which are beta roots in one frame, and then Q tilde has beta roots in the Seiberg dual. Okay, so all of them at the same time. And then let's shift it by Q, by the two star mass. Okay, and let's compute the Wronskian. So the determinant like this, right? And then you can see that this basically will be this times that minus that this times that. And you almost reproduce the left-hand side of the QQ relation that I just showed you, except that there's no twist parameter, right? Now, so turns out that so we can modify the definition a little bit, and then it will exactly lend us to the QQ system and all the Flaky equations that I've been making. So this is what Oper will do for us. So I'm just going to give you the complete definition. Is a bit complicated. I'm just going to give you the SL2. So this is the Q kind of difference version of the Oper. So I have a Riemann sphere. So we just CP1, which is equipped with the multiplication by Q. We take the coordinate multiplied by Q, right? It's a well-defined operation. And then we have a vector bundle E of rank 2 on CP1, right? And then, so in some trivialization, S will be the section. So it will be eventually the same S as I showed you before with a Q and Q plus, Q tilde. And then the Q connection will be a linear map from E to pulled back E. So essentially take your, all your sections, and then you replace U by QU. You do the change of variables. And then if you take functions that live on CP1, say some rational functions based on U, you can do this Q gauge integration, Q gauge transformation of A. So A goes to this kind of formula, and if it's the difference generalization of the formula that you know from Lie algebras, you can just Taylor expand around Q plus 1, and you get the formula that it's in the board. So this is how it works, right? So and then So what's the Oper condition? So say there's a fiber over U, and then S of U is the vector here, and then there's a fiber over QU, and A of U is this map. Okay. Now I can do two things with a vector. I can.
But that is a complex plane. Or...
Yeah. So it's a two-dimensional complex space. C2. So S of QU will be rotated a little bit, and then I can also act with my connection on my vector S. And in general, I expect those vectors to be not parallel to each other, right? So they will be linearly independent. And that's exactly the Oper condition. So if I claim that these two vectors are linearly independent everywhere on the base, then we have an Oper, Q Oper, SO2 Q Oper without singularities. It's a very natural idea, but sort of formally it's described like this. Now I want to make the
It could be relatively small, right? I mean,
what it the determinant.
I mean, no, I mean. not-
Yeah, that's right. But I mean, as long as they're not exactly parallel.
Yeah.
That's okay. So, but now I want to allow them to be parallel. So I want this to be equal to 0 at some isolated singularities, isolated points on CP1. Right, and this is how we introduce singularities. So now say that the right-hand side is now a polynomial whose zeros exactly those masses, A's, right? And also I can include together with those singularities, I can also include the tower of states, which are related by tower of those points, which are related by Q multiplication. Okay, so that will give me some extra data, some spins. I can study spin chains with I can study more complicated representations this way. And additionally, so I also add a twisted condition. So I'm assuming that there exists a gauge transformation that diagonalizes A, right, to the central element. So Z is just constant matrix with some diagonal, with some eigenvalue. Okay, now, and then if section S, let's call it Q plus and Q minus, I think available from Q and Q tilde, and Z is this diagonal. So Z from the beta equations, so the variables will be zeta squared. Then you can just compute this determinant, it will be 2 by 2 determinant, and it will be on the nose the SL2 QQ relation. Okay, so that's this geometric construction reproduces you the QQ system, which in turn is equivalent to the beta equations, and those describe the massive factor of your favorite theory. Now, since it's just comment why this is called an opera. So opera kind of part of the operator. So if you think of this Q connection as flat, meaning that there's a difference equation like that. So you have a Q difference equation in S. So if this is equal to AS, you can write it down as a certain scalar difference equation, right? And whose coefficients will be eigenvalues of the transfer matrix of SL2 spin chain. Let's not worry about it. Now, so it turns out it's also related to CS. So that's kind of one part of the story. And you can also find connection with other integrable systems that appear in the this physical mathematics world. One of them is trigonometric Schneider system. So I think Shlomo probably talked about it in his talks, right? So now let's take those polynomials of Q and Q tilde, very special forms. We just take linear polynomials. So say P1 is the root of Q, P2 is the root of Q tilde. And I compute this determinant. What do I get? I get a quadratic polynomial in U on the left-hand side, and I had say polynomial lambda is also quadratic, right? And then so you can compare the coefficients, and those coefficients will be exactly the integrals of motion. So the integrals of motion of the RS system is equal to some symmetric function of those roots on the right-hand side. So in other words, the determinant is Wronskian, you can rewrite as a characteristic polynomial of some other matrix, which is what is called the lax matrix of the integrable system. So it generates all the conserved charges for all the integrals. You have like 3 minutes, 4 minutes?
2 minutes and then.
Oh yeah, okay.
I'm not sorry.
Hmm?
5 minutes.
5 minutes.
To the third.
To the third. Excellent. Okay. Any questions? Also notice here, look at this expression. So so what is this? Like it's a very nice expression. It's supposed a classical version of the McDonald operator. So P's here are so after you do the quantization, which I'm not doing here, so that will become a difference operator in some other variable, which is not Q, this will be some other variable, other Planck constant. So those P's will shift. P1 and P2 will be the shift operator, right? So this is a finite difference operator. And then notice that classically those P's, they come from zeros, from roots of polynomials Q and Q tilde, right? So in sense, the Oper somehow contains all this information in it, right? So like it's so it's a bundle with some sub bundle, right? And the sort of the explicit information about the phase space of this integrable system is encoded in Oper explicitly, right? And in fact, there are 2 integrable systems. One is this, and the other one is a quantum. So I think here's just one more. Yeah. So this is the example for the particle. So there are 2 operators. This one and just the product of shifts. So there's a symplectic form, which is kind of this using this log derivative, right? And the integrals of motion are just the equations that tells us that the yeah, so those Hamiltonian functions are equal to some certain values. Okay, and then so if this RS model sounds a bit too exotic for you, you can take the speed of light to infinity limit, which is speed of light somehow is hiding this exponential factorization. Subtract the energy of the MC squared, and you'll get the color. Okay, so we have a little bit more time. So now, in full generality, the theorem looks like this. So we proved it with Frankel and Anton Sage and Sage, based in gems. So, well, there's some other structure which called Mura. So it's Oper for group G, right? You can write the Q connection in this universal form. So if E's are the positive roots of G, alpha checks are cartons, right? And then now we have, instead of just two Q's, Q plus and Q minus, you get as many Q's for each node of the Deakin diagram. So you take the product in some order. So you pick the order in the Coxeter element of the while group of all the reflections. You pick the order of this operator. And the problem is that there's a one-to-one correspondence between set of non-degenerate, z-twisted, GQ Opers on CP1, basically the structure that we described, and the space of solutions of the QP system. Right, so here, notice that this AGI is the cartan matrix. Essentially, the right-hand side tells you like how each node talks to other nodes in the diagram. Okay, and then so you can do other things. So I described you the spawner. So there's if you have difference, exponential coordinates in momentum part of the phase space and exponential coordinates in like an X part, then you get XXZ and TRS model, but then you can sort of take this scaling limit, right? And then in each of the corner of this diamond, you'll recover different types of models that you've probably seen before. For example, there's an XXX chain, the original Heisenberg paper, and then in the same sense, it's due to the trigonometric calendar. So there's an analog of this Oper, we call them G epsilon Opers, which in a sense encodes both at the same time, and then there are also others. Okay, so now QP system appears like Feynman was saying, right? So it jumps at you and works, and you don't know why. So this is kind of the 21st century version of that, right? So it appears in this systems, appears in the category of representations of this quantum fine algebra, quantum equivalent key theory of Nicodemus varieties, and then there's an interesting development, which I think I talked to some of you privately, that this ODI correspondence. So somehow an Opers also appear to be a central object for all.
Peter, the way you presented it just looks like, you know, something you're doing within the 2D integral system, a reformulation of the beta-Ansatz equations in terms of some
I
connection.
structured my talk this way.
But what's the relation of that to the physics setup, the gauge theory setup? I mean,
I started from gauge theory.
Did that somehow suggest? I mean, are Opers something that you can identify as?
There are more Opers than allowable gauge theory constructions, right? So we have say Guru KN. There's some inequalities, right? So like which comes from this one loop corrections to the monopole operators, right? But there are no corrections like this for Opers. And
I'm asking something sort of what's the link between this Oper construction and the physics that you showed us at the beginning with the gauge theories on intersecting brains? I mean,
but I thought
maybe I missed it.
I did not start with Hein. Okay, so
I understood the beta-Ansatz equations come out from the superpotential, but where does the Oper come?
Oper comes from considering two Seiberg dual frames.
Okay.
Yeah, so Q is the Baxter polynomial in this original frame, Gur Kn. Q tilde is the Baxter polynomial in Gur n minus Kn. So and if you have, a big, larger quiver, you can sit on one node, and you can do the one mutation, one Seiberg duality, you could do one again, and again. So it's not an involution. You'll do as many dualities in one node as the rank of the quiver. And
is this some sort of dualization of the beta-Ansatz equations? I mean, people talk about rewriting, changing variables in the beta-Ansatz equations.
Yeah, that will end up with that, right? So I mean,
it's the same kind of thing.
I mean, yes, on a level of the beta equations will end up into this change of variables, but it's not very explicit, right? So I'm almost out. I'm just out of time, so let me just make a couple of comments and we can get back in the end. So
like from taking the superconformal index, you would say I mean, it's like if you prove cyber duality in the superformal index, it's just a small subset of the subtle points of superformal index are beta equations.
Right? It was just the motivation, right? It's a development in different direction, right? So it's like, so there are more beta equations that you get from Opers than from Nekrasov-Shvili, right? So like the space of all parameters which are allowed by physics is a small subset of things that you can do for an abstract Oper. But I mean, yeah, so the reason why I started from physics is because I wanted you guys to relate to this. Okay, there's a one more application. So there's a peculiar identity for determinants of the matrix. So you have an n by n matrix, right? And then you remove one column and one row and compute its determinants. And then you remove another column and another row and compute its determinants. And then you do this removals in different order. Okay? And then you remove both, like 2 and 2. Turns out that there's this quadratic identity, right? It's called by various names. So I think just an object of Vitruvi, or use Carol for short, or Alice in Wonderland identity, right? So and then it turns out that this is the if you take this if for this matrix, it works for any matrix. The generate when the generate doesn't matter. If you take the this for the matrix, you take the Q Wronskian, then you'll get again this Q system. Yeah, sort of, and then it's related to things like structures and so yeah, I hope I convinced you that this is an interesting story. Let's make things in the slide. Okay, thank you.
Maybe I have a question. So when you, a second point, you were talking about the trigonometric RS equation. So this has an interpretation on like defect term, Wilson and Pufu.
Yeah, so this is the, so if you compute the localization to graph of the Pufu loop and it was the start theory on F3 crosses 1, then this will be this.
Yeah, I think my question is that what more the Opers tell you, and then I think if I remember this type of equation works for like loops that are in anti-symmetric implementation. And I mean,
yeah, so here you see like so the I took a very special, I took those polynomials to be linear, right? But you can take any degree, right? Or you can have like bigger metrics and polynomials can be any degree. We get some relation like this, but it's more generic, right? Than Zara's and it's like because okay, maybe it comes from some bigger model by some sequence of reductions, but it kind of gives you. So in sense, like yeah, so presumably that bigger structure will be able to allow you to study all of those higher representations as well. I think we elaborated some examples for type A. With start with a bigger matrix and then just say okay, P1 equals to P2 times Q squared, like Q, or and so on. We'll have some cancellations. Kind of this matrix will have this block diagonal form. Each block will look like what's called Slotoway slice for some choice of the orbit and so on. So there's a beautiful story, but it's there. So,
any more comments, questions? Thank you again.
Ну, я тебе, как я говорил, это не прямо, поэтому, ну, что главное условия влияют на...
Там будет свой
Нет, ну правильно, но
просто считаешь,
Почему?
нет, нет, почему? У нас там не
нам когда свой видео,
там условия,
а потом просто.
ну, конечно, нет, ну, правильно, но я имею в виду, что тем не менее, ну взяли, конечно, размеры ящика. Большой, чем ну, по сравнению с тем, что Кинг помещался, по размеру, ну, конечно.
Все-таки единица на...
Да, конечно. Нет, и более того, я согласен, что это не ответ. Я не говорю, что это ответ. Я просто поделился.
Я понимаю, это может быть.
Что просто, ну, вот это, потому что
Дальше есть.
в твоем примере есть виртуализация. Не влияет. А я пытаюсь привести пример, который влияет. Это влияет, но теперь по этому вопросу буквально в принципе поверьте, потому что проявлять и будет там такое явление, что часть летала типа границ. Ну, это вопрос. Если такое окажется, тогда вполне спокойно да, правильно, но мне кажется, что ну, все-таки само физические варианты такие, чтобы если они не ввожу только зависимость от границы, то я бы сказал, что твист или не твист, это настолько, какая мне разница, если есть конденсация, да, то я бы сказал, что нет. Тогда я в этом я не вижу выхода. Сказать, что вот так. Но это не ну да, не, ну что нет, она может и ответ действительно может раз больше. Но если он за счет мандался за счет своего, тогда это нормально. Наш такой стабильный, остальные покоряют. Но я же Эрик, я так подозрение, это еще не в этом нет, называется пытаюсь измениться. I don't see that happening. Потому что настоящий не думал, не разбирался в вопросе. Но я еще not exponential. I'm sure there really is a massive thing.
The Zoom, sorry, so.
Oh, sorry.
So that one will project to you a PC. So I don't think you have it set up to mirror.
Мне кажется, что это интересно. Спасибо за привлечение внимания. Конечно, нет. Ну, потому что, да, это та история, которую вспоминал насчет долго.
У вас там написано в работе SUSY аномалий бозон, написано там ответ должен быть константа, независимо от.
Ну да, нет, я не думаю, что есть какие-то принципиальные возражения по этому поводу. Если не так, то это же означает, что надо искать что-то такое объясняет, правда? Но иначе же как-то Нет, ну потому что, ну, я не знаю, это как нормальная физика, как локальная, вполне. Если ответ зависит от условий, это все-таки какая-то революция.
Why this is important? Oh, because this will still
Спасибо большое.
Да нет,
solve the strong CP problem in the sense that the kata would still be unphysical. That's why we are so, that's why this is so important.
Yes, but what is that?
Also, the delta MR.
What is it that impact there's physical observables, the phases of the
Well, so they claim that, the lattice people measure, what MR is, and that they are measuring somehow the sum of the two.
Yeah, it depends. Because you have to know which come up like the branch.
Right.
Yes. In that sense, it's more like a comparison question, like a physics question. Okay.
But I don't see any term like question in Supersymmetric.
I don't even know what like which physics question. I would say there is nothing special about it.
You would say that it actually wouldn't solve this problem.
That's why it's special. What it doesn't take design.
You would say lineage.
I would say, I don't know what that means. There is parameterization. You can ask physical questions. What is the risk that?
Right. Exactly. You would say it would still be generated. So the playing ball that it would not be just that ball that will happen in one game. If we set up, it would not be.
This is the. I'm very. So, to be honest, like. Every time you choose a relate all the configurations is one action. But they don't generate. It's just a random non-skipping variant, non-skipping random.
Sorry, so you would say there's more than.
We have to think about the slice. Let's think about the slice. Let's think about the slice. Let's say.
Yeah, sure.
Let's say we fix this. And we try to plot the wave diagram because we have function. So I would say. What is the wave?
Ангель, добрый день, это Аркадий. Ты вот звонила, я так мой телефон говорит. Не, а куда, кому послать-то?
Here it's possible where exactly does then there's a special light.
Хорошо. Ну, я пошлю ей, я не знаю, сможет она справиться. Нет, я же не, ну, здесь, как ты знаешь, не там. Но я пошлю. Я не знаю, я думаю, что она может с вами. Ну, в общем, я пошлю ей тоже. Значит, получается, значит, 4 людям, ну, как бы тебе, да, значит, тебе Лизималку и Нель, значит, 4. Хорошо. Нет. Да, завтра уезжаю. Я приехал 1 мая. Ну да, но не хотел вас пугать. Ну, там был, да, был, это сейчас второй воркшоп, был один сначала, но я был, да, немножко долго, да, все нормально. Ну, выглядит очень хорошо, замечательная погода. Да, сейчас просто ну и когда я вроде отвык, да, понимаешь, не, ну я был, мы были в прошлом году с Нелли вместе, ну, год назад, да, ну тогда мы не были так долго, был другой воркшоп, ну, и тогда мы вроде, да, это было в то же самое время. Да. Ну, сейчас, ну он же был, наверное, в email, да, ну да. Но если что не так, я все равно вас найду, никуда не сможете деться. Хорошо. Да, нет, спасибо, до встречи. Всего хорошего.
Right, but I guess, but so when you have MAP equals 0, yes, you do have the whole axial symmetry essentially.
There's no extra symmetry. It's a different. That's why additive renormalization is not. Because that point is not extra symmetry. If that point had extra symmetry, it would be the same.
People, I think that is what people usually imagine. It is an extra symmetry.
Exactly like that. There is no extra symmetry. This will cancel things. The master point is one. It's a random point.
Right. That's what I just started reading your papers.
Yeah, what's his name? You said that somebody can be at the same. Sorry.
No.
Okay. Because she mentioned the next. But we just picked about the symmetry. There is no extra symmetry.
With anything goes wrong.
No, even if I fix those to be positive and they're very dead, there is no extra symmetry. And nothing. There is no.
The others are positive.
There is no extra symmetry. What is that extra symmetry? You might think it will rephrase the numbers as they begin. That's why additive renormalization is allowed in multiple origins.
There's no extra symmetry, yes, but I thought that in that case, theta becomes unphysical.
It's also unphysical here, look, it's fixed. There is no difference between this point.
Okay, so you're saying that this whole story about MAP equals 0 is just correct?
Yes. It's just the random point which preserves time versus. And if the Baryons spectrum involves continuously. The Baryons spectrum is continuous. All the other observables, there is nothing. And saying that there is no data angle at that point, it's completely meaningless. There is also no data angle at this point.
It's certainly. I think I see what you're saying.
In the sense that there is a data angle, it's 0.
Right. That's certainly not what the phenomenology community thinks. So that's really
in the phenomenology
important.
community, there is a different story that is going on.
It's really important to transmit it. I think you're probably right. So.
In the phenomenology, there is different. Like there is another issue, which is that there are outcomes.
Right.
And some processes that don't see the ADGF. Electric processes they don't see the one. There is a if you not get at this point in discussion. And many electrical processes are sensitive to the direction. And that you want that one. There are time universality. Would you say that that makes zero? Would you say that that makes zero focus? So there's just something there. Sounds good as any other. I mean, that's pretty good. I think everybody.
No, I think I see what you're saying.
These additive normalization schemes, right? So the coefficient depends on, you have to integrate over these.
Right.
It's just that on the lattice, you don't know, when the lattice people tell you that they see that they're to zero, you don't know where the snag they are. How do you find them?
Кен, извини, толкаюсь снова. Я просто хотел уточнить, ну, с какого времени писать этот зум? 8 вечера?
Yeah, so my best.
Обычно было 8, я хотел проверить с тобой. 8 осталось. Хорошо, тогда я пишу 8. Хорошо. Извини, но удовольствие, зато я получаю удовольствие тебя слышать еще дополнительно. Это пока.
I know that people think that they like polar coordinates. So it seems like a special coordinate. I don't see this polar coordinate.
Right. Thanks. It's really useful. So it's half of all the lecture notes in the strong people in this tour.
No, I think it's quite special for electrowave processes. CP violation is sensitive to the determinant of that matrix.
Right. But
And
that's
that's
not
important.
how people, that's not how they interpret it. They exactly interpret it the way we said it. That's just for QCD, just.
No, I don't. Serious people said something. I don't even know what MX0 is. It's a dependent question, right?
Wow, that's one of the questions. Yes, that's exactly.
You can't
what-
even tell me if you cannot even define it. If it was a point with extra symmetry. If it's a random point, face that.
Okay, I'll double check the two past lectures. To
Yeah,
see
if you
if
see
it-
something, if you see something saying that there is an extra symmetry there. Or that some observed in the conversation is very. I think what.
Right. It definitely is, yes.
You can use the definition next seven.
Yes, absolutely, absolutely, yes. On this conception.
That's why I think that when you compare your results to CP, it's important to try to understand. That.
Right,
See
right,
this-
right, yeah,
this
yeah,
structure.
no, I can see. Thank you.
Thanks.
Right. Only this one, so.
I think one of the pictures that Misha showed, I sent Maziero. I think he was on some AMSB papers, no?
Maziero?
No?
Gidic.
It's not, the seminal paper is not, oh, it's from the 90s.
The MSB is 1990. Also, there was one by.
когда заговорил с Гений, когда я слышал вот про, ну, про Леву, да, ну ты знаешь, наверное,
Я
больше.
знаю, но последних новостей я
Я тоже, ну, я не спрашивал сейчас, ну, просто это, понимаешь, я всегда его как для меня как был образец, ну, такого здоровья. Ну да.
Нет, я знал, у него давно были проблемы, но они были как-то решены. Потом это никак не сказывается. До последнего года.
Вчера у меня там самый, ну, Саша Соловенчик, ну, ты его, конечно, наверное, не знал, но это тоже было с Володей Захарова, там в Новосибирске, 5 лет мне младше. Но, понимаешь, 5 лет это как бы уже все равно ощущение, что молодой человек, ну, не знаю, но ты понимаешь, что все равно внутри это. В Ливерморе он был, ну, базовым, в Ливерморе. Так, но у него были проблемы серьезные, тоже здоровьем. 75 лет.
А ты что-нибудь слышал о Вале Захарове?
В последнее время нет, да. Но он как бы все время был озабочен, Наташа там болеет серьезно. Когда, ну, понимаешь, обычно там ты типа день рождения, прочее, это, сказать, то есть нет такой постоянной связи, но время от времени. Но при этом это все было в эту сторону. Да. Я к тому, что мы должны быть счастливы, что вполне это.
Я каждый день сдаю с этой мыслью.
Понимаешь,
а вечером благодарю.
Ну да.
Шаббат за лишнюю неделю.
Я был на шаббате вчера в этом, у Quivers.
К ним же сейчас приехала молодая часть семьи.
Ну да.
И они же ортодоксы.
Ну, слушай, он же со мной все проделал, все по полной программе, это, знаешь, все процедуры и прочее, все было по полной, да, с чтением, пением и все такое. Да.
Понятно. Да, ну вот, получил удовольствие.
Ну да, не, ну, понимаешь, я еще там очки забыл в машине, я даже там, понимаешь, я даже прочитать там по-английски, там, на иврите, я это, конечно, тем более не умею. Не, ну как-то, понимаешь, не знаю, Дэвид, ну я его помню, там скорее ребенка больше, но, видишь, у них какое-то было явно изменение отношений. Рома вообще воспитывался сурово. То есть, ну, они к ним приехали, там, ну, я помню хорошо, что Алиса уже была вполне, ну, как бы, она немножко младше нашего Андрюша, они вместе играли, там, понимаете, все. А Дэвид был самый это избалованный. Ну, потому что, смотри, ну, Рома и Алиса, они все, они же получили образование, понимаете, а он же 1 год проучился и все.
Я помню, он со мной разговаривал, они там приезжали к нам, через 2 года, он меня рассказывал, что вот я подал на Neuroscience, хочу пойти в университет Миннесоты.
Он был в университете?
Ну, я знаю, да. Я ему там немножко рассказал, что это такое, и все. Да. И для меня, честно сказать, было очень, даже я не понял, почему он год всего проучился и бросил. Он не произвел на меня впечатление такого уж совсем легкомыслия.
Ну да, но видишь, ну как бы он пошел вот в это religious стадию серьезно, то есть он, я понял, то есть он, ну правильно, но эти же, смотри, и Рома, и Алиса, они тоже достаточно религиозные, и были.
Нет, Алиса завязала,
ну правильно, ну была. Да, но Рома тоже был в Израиле, там прочее, понимаете, и в этом смысле все-таки это немножко, не знаю, это.
Ну, это возьми сын Никита Некрасов.
Да.
Уж какой он был выдающийся. Он же на всех олимпиадах уже вот.
Горе.
Да, который сейчас вот
да.
учится.
Да.
Он на все олимпиады ездил математические, на все летние лагеря.
Ну да, Никита же сам этим занимался.
Да, и он так этим всегда рассказывал, что вот там, то все. год проучился и ушел на психолога. Сменил.
Это Никит сказал. Ну, у нас же М на психологии.
Но она не собиралась никогда в математику.
Нет, она не собиралась. Нет, там это называется департамент, ее называется Science Brain, то есть он такой довольно, там много чего проходит, но психология то, что ей реально нравится. Человек была в школу, там, элементарную школу, они это как бы часть.
Я знаю, Аня же училась, она училась бесконечно. Первые 4 года там.
Нет, это 4-й год.
Она уже пошла в психологию, потом.
Ну, да, серьезно же.
Thank you very much for the invite.
It's not me. You didn't want me to come? No, I mean, I am kind of.
But good to see you. Thank you very much for coming, for giving a talk. You are flying back to London.
Yes, yeah. Well, I sort of,
Yeah, and that I'm glad to see you. Glad to see you after so many years.
I know, yeah, it's been too long. See you soon, hopefully.
Okay, have a nice way back.
Okay, so I think it's time to start. So next up is Shlomo, who is about Starship Quivers Symphony.
Thank you very much. So first, I want to thank Misha, Zor, and Thomas, who is not here, for organizing this very stimulating meeting and for giving me the opportunity to talk. So I will be talking about some program that we have with a lot of collaborators over the last 5 years. But I will focus on a very short paper that we all have written about 2 months ago with Silviu team, which kind of summarizes the whole program and gives maybe the simplest example of it. So what is it about? So about circa SUSY at 20, there was this amazing progress due to cybering and which was followed by many other people, of discovering a large plethora of infrared dualities. And in this talk, I will call these dualities in-dimension infrared dualities. So in these setups, you start from 2 quantum field theories in certain number of dimensions. You deform them in some way, and you flow to some infrared fixed point. For this talk, it will not be important that you flow to exactly the same fixed point, but that you flow to a certain conformal manifold. The same conformal manifold in the 2 cases. That means that there is an exactly marginal deformation which connects you one point to another. So there are various varieties of this type of dualities. For example, one description, say QFT2 can flow and QFT1 can directly describe the fixed point, or both quantum field theories can describe directly the fixed point. So this is sometimes called a conformal duality. For example, n equals 4 is such a case, and there are more complicated things. So I mentioned this, I changed the name of these dualities to in-dimension dualities, because what we're going to discuss is something slightly different. And this type of phenomena I will call infrared dualities across dimensions.
Excuse me, why it is duality if they flow to different theories? Well, in cyber-Griffin case, I understand. You take 2 different theories at the UV, descend down, and they become identical. So that's duality. Right?
So I identify the theories living on the same conformal manifold. I can kind of think of it as a single theory. Of course, it's not a single theory, but I always can tune parameters in the UV so that I will hit exactly the same point. Just the fact whether I hit the same fixed point or not will not be important for what I'm going to talk about. To an extent. Okay, so this idea of across-dimension dualities is slight generalization of these infrared dualities in a certain number of dimensions. And here we start from 2 descriptions, 2 field theories living in different number of dimensions. And one theory will compactify on some space,
And in this talk, we will start in 6 dimensions and we'll compactify on the 2-dimensional surface, but it can be generalized. And we flow in the infrared to a lower dimensional quantum field theory, which can be an interesting quantum field theory or boring one, but we flow to something.
But then it means it's kind of holographic effectively.
No, there is no holography.
Where's us dimension?
So you lose the other dimension, you compactify, you go to low energy, to energies below the scale of the space.
So it's a compacting.
Exactly. And you can have directly description of the same theory in lower number of dimensions, and you flow to the same again conformal manifold. If that happens, then we say that the 2 theories are across dimensions dual to each other.
But then effectively at larger scale, they are the same dimension, right? No, because if I'm looking at this as larger,
Not smaller scale.
larger scale. Because when I do not see compactification, no, I try to make dimensions the same. Right?
Okay, larger distances, smaller moment.
Larger distance scales.
Low energies are the same.
Yeah.
High energies are.
So low energy.
So one thing I want to emphasize about these types of dualities across dimensions is that these 2 theories, QFT1 and QFT2, it is kind of a trivial comment, but I think it's important to make it. These 2 have to be really different definition of theory. So, for example, if I only have a QFT1 and I say that it flows to some 4-dimensional theory, and I predict the existence of some 4-dimensional theory starting from a 6-dimensional one, I can predict various anomalies and other properties of these theories. I will not say that this theory is dual to this one. It is just an infrared fixed point of this flow. So I say that there is a duality if there are 2 different descriptions of the same fixed or the same conformal manifold in the infrared. Otherwise, claim of duality has no really content. Okay, without this different description of the lower dimensional theory, sometimes these lower dimensional theories are called non-Lagrangian CFTs because the higher dimensional starting points, if they are in 6D or in 5D, they are strongly coupled CFTs. We don't know much about them. They don't have a Lagrangian description. So then also the lower dimensional theories are non-Lagrangian. So in this talk, we will not be discussing non-Lagrangian CFTs. We will always have this other description using vanilla quantum field theory. So we'll have this across dimensional duality.
Excuse me, and can you uplift, let's say QFT2 is 6-dimensional, and QFT1 is 6-dimensional, QFT2 is 4-dimensional. Can you uplift it to 6 dimensions?
So this is one of the questions I will ask and not answer in this talk.
Okay.
But let me tell you what are the goals of this program, and this could be one of the goals. So what are the goals of such a program? So first of all, there is a lot of in-dimensional dualities that we know, a lot of interesting other strong coupling effect in 4 dimensions that we know, such as emergence of symmetry. And this type of geometric engineering of quantum field theories in lower dimensions will allow us to systematize our understanding of these types of theories. So this is one of the goals.
No, but when you're saying that it's different series, look, you started say from 6 dimension, and then you compactify a couple of dimensions, and it could be that the series after compactification is equivalent to your 4-dimensional series up to a definition of cutoff, right? Could, I mean, say UV cutoff, you make a connection between them, right? So then the series could be not really different, or besides, kind of UV cutoff.
Even if you start from some material in 6D, you just do a reduction of the theory, and you can understand what.
Not just put 2-dimension to be compact, right? And they would claim this the size is my UV cutoff, and compare with 4-dimensional series, it could be equivalent, right? Equivalent from the very beginning. At this
it could be, but since we know very little about these 6-dimensional theories, we usually cannot say.
I see. So
if we would have a Lagrangian in 6D, or say we start from 4D and we have a Lagrangian and compactify down to 2D, and we get some effective field theory and we can directly relate it,
Yeah.
that would be the case. But in these cases, we cannot
So,
say.
so this would be not of interest for you. Right?
No, yes, I cannot say if that is like that,
Yeah.
or it is something more complicated because we don't know much about this stuff. And finally, another goal. So these things of systematizing our understanding of dynamics in 4 dimensions.
Press the wrong button.
I pressed the wrong button. No, I think I just talked too much.
Now it's
It's back. Sorry. I need to switch slides fast. Okay, so and the final goal is to better understand strongly coupled CFTs in general number of dimensions. So one idea would be to understand all the possible compactifications of higher dimensional theories down to say 4 dimensions. And then from this information of all the possible compactifications, try to understand the 6-dimensional theories themselves. So I will not discuss this, but this is a big goal behind this problem. So again, today we will discuss compactifications of 6-dimensional theories down to 4 dimensions. And in particular, we will discuss a family, an infinite family of 6-dimensional theories. I will say a little bit more about them, labeled by this number n, for any value of this number n, and we'll compactify this infinite sequence of 6D theories on any Riemann surface with any background fields possible. And we will find the cross-dimensional duals, which are just vanilla n=1 simple Lagrangians, which have this form. So we'll have 4-dimensional theories, which will be labeled by the choice of the 6-dimensional theory and the choice of the compactification surface. But everything will be completely Lagrangian. In some sense, I will try to convince you that this is probably the simplest example of a cross-dimensional dualities that we know about at the moment, but it is extremely rich and connects to known physics and can generate new physics possibly. Okay, so before I start with this, discussing this particular sequence of theories, let me tell you what we know, what type of cross-dimensional dualities we're after. So a canonical example of such an cross-dimensional duality is compactification of a certain 2,0 theory in 6 dimensions of A1 type on any Riemann surface. And this appeared in a seminal paper by Gaiotto many years ago. And the claim is that the cross-dimensional dual of this theory is just a variety of conformal gauge theories with SU2 gauge groups and very simple matter. Trifundamental chiral superfields in trifundamentals of SU2s glued together by gauging various SU2 symmetries. This is this type of duality. We start in 6 dimensions with this 2,0 theory. We flow to 4 dimensions, and then we have a conformal dual of this theory. So this is type of duality we're after, but for a very large class of 6-dimensional theories, not for a particular one. If you take other 2,0 theories, we know we can describe the compactifications, we can describe the fixed points, but typically we don't know anything about, like we don't have an cross-dimensional dual. We don't have a 4-dimensional Lagrangian which flows to this point. There are many examples in which we know such cross-dimensional duals, and some of them were discussed in Emily's talks. And there are some other scattered examples, but in general, we don't know of a cross-dimension.
But in first example, quivers are like a composite object, or in which appears in first example.
It's just usual chiral matter, chiral multiplets, and you gauge. You have a lot of gauge groups, a lot of matter, and the gauging is conformal. So these are just vanilla gauge theories. Okay, so let me start with a description of what are the 6-dimensional CFTs we start with. Then I will discuss the cross-dimensional duals and what is the physics that we can deduce. So all the information about the 6-dimensional theories we will need is written on this slide. So the SCFTs we will discuss are so-called Dn+3 minimal conformal matter theories. And they can be engineered in M theory by looking on a single M5 brane probing some sort of a singularity. So we have this number n defining these theories, and some things we know about these theories. For example, what are their symmetries? and the various 't Hooft anomalies for various symmetries and so on. Another thing that is known for these theories is what happens if you compactify on a circle down to 5 dimensions. So for these particular theories, you can do compactifications in different ways. You can turn on various background fields, holonomies, while you compactify, and depending on what you do, you actually get different gauge theory descriptions, effective gauge theory descriptions in 5D. So the theory is completely strongly coupled in 6D. We don't know how to describe it, but once we compactify on a circle, depending what we do, there are various descriptions using these types of gauge theories with a certain method. So this USP2N gauge theory description will be useful for us. Again, these theories are infrared free in 5 dimensions, so you should think of them as being UV completed by the original 6D theory. We will compactify the theories on surfaces with punctures and holes in the Riemann surfaces that on which we'll compactify. And to define a puncture, we will need to define boundary conditions of the punctures. Again, since the 6D theory is strongly coupled, it's hard to define what the puncture is directly in 6 dimensions, although it's possible. So a way to define a puncture is to compactify to 5D. Then you think of a puncture as being as a very long cylinder which you cut at some point in 5 dimensions, and then you specify various boundary conditions. So there are various choices of boundary conditions. One is called maximal, where you give Dirichlet boundary conditions for the gauge fields at the boundary. And then the 5-dimensional gauge symmetry becomes a flavor symmetry associated to the puncture. And you give other fields what you need to do in order to preserve some amount of supersymmetry. There are other choices of boundary conditions, and they can be related to this maximal one through certain RG flows. This will be not important for us. The only thing that will be important that when you reduce the symmetry by certain RG flows triggered by VEVs to some operators which are charged under this puncture symmetry, there is some type of a minimal puncture, which in this case will have an SU2 symmetry, and then you can also close that puncture down to nothing. So that's all I need about these theories. Yes.
So the holonomy that you use to go to 5 dimensions becomes part of the data of the puncture.
It affects the puncture. So very good. So if we start with the holonomy, which gives us USP2N gauge theory, then the punctures will have USP2N symmetry, the maximum punctures. If we do that,
around the puncture.
The holonomy around the puncture, yes. Or you will get SUN+1 here or SU2 to then. So different choices will give you different punctures. Okay. In class S, we don't have that, but in more general compactifications of 1,0 theories, we often have different types of punctures. Okay.
Who knows the space of punctures?
No, but it's an open problem. So this is like this is an active area of research.
Even in 3D, we don't know this. Even in 2D, we don't know the space.
Yes, even in class S, we don't know the punctures. So the punctures that were classified when you compactify 2,0 on a circle are punctures which preserve n equal 2 supersymmetry in 4D. But punctures which preserve only n equal 1 were not classified. It's actually a hard problem. So there is no classification. These are just some facts that are known, but there is no claim that these are exhaustive facts.
Even for 2 free fermions in 2D, we don't know the space of boundary.
Yes, all of these, like what happens, what are the possible boundary conditions are extremely interesting problems, questions, and I think they're, answering them in these setups is extremely important. I will not talk about
even in 2D for 2 free fermions. Nobody knows the space of boundary conditions.
Nobody tried to say, or nobody knows.
Nobody will ever know.
Never say never. Okay, so let me continue. So these are the 6D theories we start with, and now I will give a claim of a cross-dimensional duality. I will not derive it, but I will give you evidence or discuss what is the evidence for that. There is a way to derive this type of a cross-dimensional duality semi-systematically, but I will not have time to go into it. I mean, it's not going to be an important point of this talk. So the claim is like that. If you take as QFT1, this 6-dimensional theory, and you compactify it on a very particular set of surfaces, which are just spheres with a lot of punctures, which are these minimal punctures that we mentioned before with SU2 symmetries, and some value of flux for the global symmetry in 6D supported on this Riemann surface. In 4 dimensions, you get a very simple gauge theory, which is just SUS minus n plus 1, where S is the number of punctures, n defines the theory in 6 dimensions, with particular type of matter, fundamental and anti-fundamental fields, and fields in the anti-symmetric representation, and certain superpotential.
What is N?
N is like, it comes from the type of the 6D theory you start with. Okay, so that's you choose what type of singularity your single M5 brane probes in 6 dimensions. That's N, and it enters into this theory.
So again, the middle node is SU, and these are
SUS minus n plus 1.
and these arcs are adjoint and not
These arcs are fields in anti-symmetric
So, and the
representation.
bar.
And these are just fundamental symmetry.
So this S has to be large enough?
Yes. So if S is not large enough, then we don't know what you get in 4 dimensions. And again, this is known from other examples in class S. If you compactify with not enough punctures, you get some type of a weird theory that we don't know how. Maybe it is gapped. We don't know what it is. So it has to
Can
be.
you choose n equals 0?
No, n equals 0. You can. The minimal value of n is equal 1. Formally, you can, and I mean, we can discuss what it is, but it doesn't correspond. Well, it's kind of a trivial theory in 6.
N equal 1? Okay.
Again, I'm talking.
You check your question statement, right? Every time the statement is doubtful.
Actually, you can choose n equal to 0, then the theory in 6D is actually
Okay, but they can equal 1. Then you are saying that it would be S, right?
It will be SUS.
Yes.
That's right.
Oh, but what is the mystery in this program? You previously said that it's a Lagrangian boundary condition. We have a Lagrangian 5D theory.
No, but that is if you compactify, that's actually the semi-systematics that I'm not going to talk about. So in that case, you can semi-systematically understand by compactifications on 2 punctured spheres.
Yeah, two spheres with 2 punctures.
Yes. You need to understand, because of this flux, and they don't want to get into it, you need to understand the domain walls in 5 dimensions. In addition to these punctures, you understand these domain walls, and then you're in business. That's actually a starting point of how you derive these things, but I don't want to do it. Okay, so this is a claim. And just to discuss it a little bit more, so we have a superpotential. There is an SU2S symmetry here, and there is another SU2N plus 6. We turn on a superpotential. It in general breaks this SU2S to some subgroup. And if you analyze what you get SU2 to the power S global symmetry from the superpotential. So you can draw this kind of a star-shaped, in a star-shaped way, the quiver I had before. So in a sense, the quiver theory that we obtained has the shape of the compactification surface. Okay, so that's why we call this the quiver star-shaped quivers. Maybe there is a better name. COVID-19. Okay, so what are the checks that you can perform of this type of a duality? And the checks are the usual checks that you perform of in-dimensional dualities. So you can check, for example, symmetries of the theory. You can see that the symmetries agree that with the symmetries you expect from 6 dimensions. The symmetry in 6 dimensions is this one. The one you see in 4 dimensions is a smaller one, but actually that symmetry is broken by the boundary conditions at the punctures and the value of flux, and that is the symmetry that you actually expect if you analyze it. As we discussed, there are puncture symmetries which are SU2 to the S. So for each puncture, we have a factor of SU2. You can check various Hooft anomalies and conformal anomalies, compute them by compactifying the 6D theory or directly in 4D, and they agree. We claim that this theory corresponds to compactifications on a sphere with S punctures. So in general, we expect the theory in 4D to have exactly marginal deformations, number of which is the dimension of the number of complex structure moduli, which in this case is S minus 3, and it again agrees. And there are various other consistency checks that we will discuss soon. We will see that this type of constructions predict in-dimension dualities, which will serve as consistency checks of all of these constructions. Okay, so we will get to that soon. Now, we have discussed compactification on surface, on a very particular surface, on a sphere with some number of minimal punctures, but we want to build theories corresponding to arbitrary number of punctures. To do that, we notice the following thing. So we turn on some superpotential, which broke the SU2S symmetry down to SU2 to the power of S, but we can turn on some less generic superpotential, which will break the same symmetry to a larger group. For example, if you take S to be 3n, you can preserve USP2n to the power 3. Okay. If you remember, USP2n was the symmetry of a maximal puncture. So here it looks like we would obtain a theory which would naturally associate to a compactification on a sphere with 3 maximal punctures. Each one is has USP2n symmetry. So the picture is like that. We compactify on a sphere with a lot of minimal punctures. We have exactly marginal deformations. We can tune them to some special values. And then the punctures, in a sense, collide and build bigger puncture with bigger symmetry. Okay, so here is an example. So we have this conformal manifold, big conformal manifold of a sphere with a lot of minimal punctures. And then somehow the conformal manifolds of other types of spheres with other types of punctures are subloci of this conformal manifold. Okay, so this is something a little bit surprising if it is correct. That's not how it usually works, but in this case, it seems to work in this way. Okay. So there are various questions that you can ask following this picture. For example, in this picture of colliding punctures and getting higher USP groups for punctures, there is no limit to the number of punctures you can collide. In particular, you can get USP symmetries which are bigger than a maximal symmetry. And everything seems consistent with that, but I don't know what the physical meaning of that is in geometry.
How can this be?
How does
What's the boundary condition? How can you?
Yes, so I don't understand it as a boundary condition. This is a statement about field theory you get in 4D. So the 4D conformal manifold seems to have loci where you have bigger symmetry than the maximal puncture symmetry. And that loci behaves as if you have a bigger puncture. But I don't know how to explain this geometrically. I have ideas about that we can discuss, but this is a puzzle at the moment.
Can you think of it as an irregular? What would be irregular?
It might be an irregular puncture. It might be something else. Again, I don't know. Maybe it's some other type of puncture which is not directly related to the maximal puncture. Another thing that you can ask, okay, since you can have any USP symmetries, what is special about the maximal puncture symmetry? So what is special about the maximal puncture symmetry when you collide n such minimal punctures is that the anomalies are such that if you gauge 2 such punctures, you don't break any symmetries. Okay. So there is, for maximal punctures, you can glue naturally these punctures together to form larger Riemann surfaces. So what does it mean to glue punctures? So when we had a puncture, we basically had some boundary conditions and we froze and gauge fields. So to glue punctures is to undo these boundary conditions. Is to gauge the symmetry and maybe to introduce some superpotentials and maybe some other fields. So what is important, there are different types of gluings that one can discuss, different ways to undo these boundary conditions. So one will call S gluing, another phi. The details are not important, but what will happen is if we glue 2 surfaces along a puncture such that one is associated to some value of flux for global symmetry in 6D and another to another one, for S gluing, the fluxes will be subtracted, and for phi gluing, the fluxes will be added up. Okay? This is something which will play a role in what follows. So once we understood these theories corresponding to compactifications on spheres with maximal punctures and gluings, we can glue the theories into higher genus surfaces, for example, to anything basically. And again, once we do that, we need to perform various checks of anomalies and symmetries. For example, if we glue 2 3-puncture spheres together, we obtain a theory cross-dimensional dual to genus 2 surface with no flux. So we can check the anomalies that they agree with this value of flux, but also this compactification doesn't break any symmetry. We don't have flux, we don't have punctures. So this theory has to have somewhere on its conformal manifold a locus with enhanced symmetry, with the full 6-dimensional symmetry appearing. And you can check that this actually happens. Again, I will not go into detail, but you can check this kind of statements by computing various supersymmetric partition functions. Another thing you can do, once you understand three punctured spheres, you can glue them in different ways together to form higher genus surfaces. So there are many different ways in which you can do that. All of them have to give the same theory, because by construction or by the claim conjecture of a cross-dimensional duality, all of them have to be a cross-dimensional dual to the same theory. Okay, so here is an example of a particular theory. So here we take n equals 1. In this case, the symmetry in 6 dimension actually enhances to E8. This theory sometimes is called the E-string theory. And if you follow the rules of the game we have outlined, this is the quiver that you will obtain. It is a conformal quiver. It has SU9 symmetry, but the claim is that somewhere on its conformal manifold, this SU9 enhances to E8. And again, by performing various computations, you can see that they are consistent with this claim. So here is an example of an in-dimensional duality that you will derive from these cross-dimensional dualities. Again, by gluing these punctured spheres in different ways, you can obtain different types of theories, which are a cross-dimensional dual to this one, and they should be in-dimension dual to each other. Okay, so in this type of geometric construction, you also explain the cross-dimensional dualities, and the idea is, in general, the following. If you have a compactification on some Riemann surface that you can build from smaller Riemann surfaces, this is a geometric operation of gluing these Riemann surfaces, then the cross-dimensional dual theory that is corresponds to the full surface is built from these small pieces using field theory operations of gauging symmetries and turning on superpotentials. And breaking the surface in different ways to pieces should be equivalent, and that's how you derive a cross-dimensional duality. Since I'm out of time, I will run very quickly over the rest of the slide. So you can also do this other type of gluing, of phi gluing. I didn't discuss the flux, but you can obtain a sphere, a genus 2 surface with a larger value of a flux. You can deduce the value of the flux and see that it is consistent again with anomalies and symmetries and everything. So in the next couple of slides, I will just discuss some very simple type of physics that you can deduce from these cross-dimensional dualities. For example, you can consider compactification on a 2-punctured sphere, not on a 3-punctured sphere, as we discussed. From the structure of the quiver that you see here, you see that it has this SUN+1 gauge symmetry, and we mentioned that SUN+1 can be a symmetry of maximum puncture. So it's natural to break this theory into 2 pieces. This is a tube theory, a 2-punctured sphere. And it's natural to conjecture that it is built by gluing together 2 tubes with 2 different types of punctures. And if this is correct, the cross-dimensional duality here is very simple one. You start from this theory, from the 6-dimensional theory on this surface, and you get just a West minimum. And from that, taking this type of understanding with the rest of the talk, you can start building theories corresponding to various compactifications. For example, the SQCD in the middle of conformal window will be a cross-dimensional dual to the compactification on this type of a surface. And various dualities, cyber dualities, will be related to various geometric operations that you can perform. And here is an example of S-confining dualities, which appeared many times in this conference. And in this language, this S-confining theory corresponds to some type of a tube compactification, and there is some game with the flux that you can perform, and you can show that the geometry behind this quiver and behind this quiver is exactly the same. So if we would not know cyber duality, we would predict it by this consideration. Of course, to start even discussing all these things, we needed to know cyber duality, so this kind of logic is not well. Okay, so let me finish with the following comments. So the one message I want to make that in this particular set of cross-dimension dualities, we can explicitly write Lagrangians for any types of compactifications, and the shape of the quiver theory basically has the shape of the compactification surface. There are various other things that you can do, which I will not discuss. So we discussed in-dimensional dualities and the cross-dimensional dualities. You can discuss also something which you would call 6-dimensional dualities, where you start in 6 dimensions with 2 different theories, compactify them on 2 different surfaces, and get the same quantum field theory in 4 dimensions. So these things we don't understand very well. There are various examples of these 6-dimensional dualities, but the situation is, as was the situation before Kyoto with n=2 dualities, we have many examples, but we don't understand any systematics of them. So the systematics probably should come from string theory on M theory. And maybe if there will be a SUSY in five years, we should discuss it. So that is the picture I want to leave you with, that there is a lot of physics that interesting strong coupling physics that we know about in lower number of dimensions. And it seems that it all stems from higher dimensional physics if we compactify it and we understand these compactifications in various ways. And so this is my summary. Thank you.
Questions? Okay, I don't want to take much time, but I do have a question. So it's very interesting that you have this small, I mean, minimal puncture that colliding with it seems to work as a maximal puncture because you can do. I mean, in the logic of IGT, like if you look at this as a defect, does it satisfy some difference equation which is peculiar, that has this feature that when you collide this defect, you get a full thing? I mean,
that's right. I don't know why it works here. I suspect that it is because it's somehow related to the fact that the symmetry is USP. You know, in classes it doesn't work because the symmetry is SU, but you know, even group theoretically, you can see that, you know, when you like the basic operators which are charged under the symmetry are in fundamental. And if you just collide these punctures, you just add up these fundamentals to a bigger fundamental. So some magic happens with this USP symmetry.
I see.
So I don't.
Logical string something happens with the USP thing. It's a bit
Yes,
like
so it's some magic due to USP. That's nice.
Question? Okay, let's thank Shlomo again. Our last talk. Have slides?
I do have it, yes. And I sent them to Megan. These are my slides. Yes. And how do I sorry.
We have Silviu Pufu talking about instant effects on a standard strings from Nitta.
Okay. Thank you very much for the invitation to speak. It's an honor to be the last speaker at this great conference. I will talk mostly, well, partly about this paper, recent paper with Victor Rodriguez and Ethan Wang, was also mentioned earlier work with these people, Simon Binder, Chester, Michael Green, and Sangha Wen. So this talk is about a quantum field theory, particular conformal field theory calculation that has a string theory interpretation. So if you don't like string theory, you can focus on the quantum field theory calculation. So in string theory, we study scattering amplitudes. In conformal field theory, we study correlation functions. And in the last few years, there's been a lot of progress on quantitative relations between correlation functions in conformal field theories and scattering amplitudes. And in particular, this progress used a variety of techniques, supersymmetry being playing a very important role. So supersymmetry, supersymmetric localization, crossing symmetry, analyticity of correlators in mailing space. I'll explain that. I'll mention that later. Use these techniques to compute CFT correlation functions at large N, and from that to extract scattering amplitudes of gravitons in 10 dimensions in flat space. So far, up until the last paper that I'm going to talk about, these gave many very impressive checks of results that were already known. And in this talk, I was very happy I was able to find a calculation that gives a new string theory scattering amplitude that's obtained from a correlation function in N=4 superannual theory. So what's new? So the new thing is a correlation function where we have a half BPS Wilson line, or it could be a Tupf line or Wilson Tupf line in N=4 superannual, as well as two local operators whose positions are being integrated in a way that the whole thing preserves supersymmetry. And I'll explain what the answer for this correlation function is in a very strong coupling limit of N=4 superannual. I'll say what very strong coupling means in a couple slides. And I'll also discuss the implications of this correlation function for scattering of gravitons off of extended objects, fundamental strings with D1 breaks. So what's the role of supersymmetry? Well, it's a big role. It makes supersymmetric localization possible. It imposes constraints on correlation functions in superconformal field theories. It imposes constraints on scattering amplitudes in string theory. And in this talk would be N=4 superannual, so maximal supersymmetry makes the calculation simpler and actually possible. So the plan of the talk is this. First, I'll review for context a story about 4-point integrated correlator in N=4 superannual and its relation to the scattering, a 4-point scattering of gravitons and their superpartners in 10 dimensions. And hopefully this is going to make the second part of the talk more believable. In the second part, I'll talk about this integrated correlation function of two local operators in the presence of a Wilson line, Tupf line, and its interpretation. So that's the plan. So let me describe this context that I mentioned. So in 10 dimensions, there's an effective action. It starts with the Einstein-Hilbert term and its supersymmetric completion, of course. But there are higher derivative corrections. First correction is written schematically as r to the 4th. It's a specific contraction of 4 Riemann tensors, as well as its supersymmetric completion. Then the next term would be d to the 4, r to the 4, so 4 derivatives and 4 Riemann tensors, 6 derivatives and 4 Riemann tensors, and so on. And well, it's kind of an embarrassment that we don't actually know all the entire supersymmetric completion of this Riemann to the 4th. So this is the first correction to 10-dimensional supergravity. Comes from string theory. We don't know what it actually is. In any case, this action can be used to compute 4-point scattering of gravitons and their superpartners. And one can show using supersymmetry that this 2-to-2 scattering takes the following form. There's some prefactor that depends on the polarizations of the gravitons, or depends on which superpartners we're actually considering, times a function, a single function of the Mandelstam variables S and T. So this is a consequence of supersymmetry. So the only question is, what is this function, f of S and T? Just one function. At small string coupling, G string, one can open Polchinski's book and equation 12.4.30 is this formula, your source superior amplitude, some ratio of gamma functions. So that's known, and well, next correction to it is also known. Well, not a whole lot beyond that. What one can do with this is to expand it also at small energies, so small momentum, small STNU. And in that case, the first term looks like 1 over STU, and this is interpreted as coming from supergravity tree level diagrams. Then the next term is a constant. This is interpreted as coming from a contact interaction of this Riemann to the 4 term. The next term, proportional to S squared plus D squared plus U squared, comes from the contact interaction with the D to the 4 to the 4 vertex, and so on. So this is the interpretation, and one gets zeta functions that I'll also appear later. Another possible limit that one can consider, instead of considering small string coupling, one can just consider finite string coupling. So finite value for G string and finite value for the expectation value of the axion in 10 dimensions, but only small momentum. And in that case, the first term again comes from a supergravity tree level diagram, the next term from Riemann to the 4th. Then there's like a one loop contribution, one loop supergravity contribution, then a contact interaction from a D to the 4, R to the 4 vertex, and so on. These are the first few terms. And people have thought about this a lot and figured out that the coefficient of this Riemann to the 4 is a function, well, is a function of the coupling of tau. And it takes this, it's an Eisenstein series, proportional to the Eisenstein series E3 halves. So I'll define it on the next slide. And then the coefficient of this D to the 4, R to the 4 is an Eisenstein series E5 halves. And then at higher orders, they're more complicated functions. What are the Eisenstein series? The Eisenstein series of ES is given by a lattice sum. So if tau is tau 1 plus I tau 2, it's a sum of tau 2 to the S over m plus n tau absolute value to the power 2s. And for example, this E3 halves, its expansion at small g string. So the tau is chi plus I over g string. So the expansion of small g string has 2 perturbative terms and an infinite number of non-perturbative contributions. So they're all packaged here in this Bessel K1 function. If we expand this at small gs, this is going to have exponentially suppressed contribution, instanton contribution. Last term, non-perturbative. Finite number of perturbative corrections, infinite number of unperturbative. Okay. So that's the scattering amplitude. Now, on the other hand, we have n equal 4 super-Yang Mills. N equal 4 super-Yang Mills has a vector field and 6 scalars, fermions, and adjoint of the gauge group, which I'll take to be SUN, with some gauge coupling, and we can define a complexified gauge coupling, which is theta over 2 pi plus 4 pi I over g squared, which will be identified with the same tau that appear scattering amplitudes. And of course, there's the Tuff coupling g squared now. And there are 2 limits one can consider. The usual limit is the Tuff strong coupling limit, where one takes n to be large with the Tuff coupling fixed, and then takes the Tuff coupling to be large. But in this talk, I will use a different limit, which I'll call the very strong coupling limit, which will be tau fixed, so theta fixed, g fixed, and just n to be large. In this limit, the Tuff coupling will automatically be large. In the Tuff strong coupling limit, necessarily, if we keep lambda fixed, as we take n to infinity, g will go to 0. So in that sense, this limit, the very strong coupling limit, is more strongly coupled than the strong coupling limit. And n equal 4 super-Yang Mills has operators. One of the simplest ones is this quadratic operator in the scalar fields, which has scaling dimension 2. It's half BPS. It's actually in the same multiple as the stress energy tensor. It's a superconformal primary of the stress energy tensor. And in ABS-CFT, This operator is dual to fluctuations of the metric and the 4 form. The A gets 5 times that's 5 back. Now there's a connection between the CFT correlators and the scattering amplitudes, and the connection is described in this diagram. So I'm going to go a little bit through it, but pretty quickly, because the only purpose of this, I'm not going to explain this, I'm just trying to convince you, trying to tell you what the connection is. So we have the 4-point function of this operator O, which again, due to supersymmetry, can be expressed in terms of a single function T of, I guess I don't have the formulas for UMV. These are the conformally invariant cross ratios of the 4 coordinates of the 4 points. So essentially, superconformal word identities imply that this 4-point function is what it would be in the free theory, plus some prefactor that depends on exactly the indices that we choose for these 4 operators. I'm a single function of U and V that would also depend on tau and tau bar. What one can do with this 4-point function, so the 4-point function is in some sense, could be thought of as the scattering amplitude in ADS. So roughly, we consider this as ADS space, as a cylinder, and we create some wave packets close to the boundary. And we create the wave packets by acting with the operators in the conformal field theory on the boundary. The wave packets go and interact in the bulk, and then they go back to the boundary, and then we measure them. That's why the CFT 4-point function should be thought of.
But normally, when you consider, say, relation between correlators and correlator, usually implies this reduction formula. So you can factor out, propagation. Right. So when you're saying that's equivalent to this, so do you have this factorization as well?
There exists a formula, yes. Yeah,
there is a formula.
Yeah. So the difference between this and that, you could think of it as like different LSZ factors. What happens is that we have the CFT correlator that can be expressed in terms of this function T. It's more convenient when we think about holographic theories to think about the Mellin transform of this function, which is a function of 2 variables, S and T. And then there exists a specific formula where we take a limit of this function, M of S and T, and we get the scattering amplitude in flat space. So there's a precise limit where we can take the radius of ADS to infinity. If we take the radius of ADS to infinity, it's as if we're taking n to infinity. So as we take n to infinity, we obtain from this correlation function, we obtain the flat space scattering. Okay. Now, another thing on this diagram is this arrow over here, which is this. So one can obtain some constraints on this function T using supersymmetric localization. How does this go? So we have the n equal 4 theory in flat space, but we can also study it on a round sphere. And on a round sphere, we could also deform it by squashing the sphere or by adding some mass parameter. And then one can take derivatives. So this would be an n equal 2 preserving mass parameter. One can take derivatives with respect to the mass parameter, or respect to the squashing, or respect to tau and tau bar. And obtain some integrated correlation functions on the sphere. And this is what we worked out in these papers, that if we take the logarithm of the S4 partition function, you take 1 derivative with respect to tau, 1 derivative with respect to tau bar, 2 derivatives with respect to the mass. There's a specific formula so this is given by an integral of this function T with some measure that preserves supersymmetry. The same thing happens if we take 4 derivatives with respect to the mass. Good. And the last thing I want to explain about this diagram is this arrow over here, which says that at each order in the derivative expansion in the bulk, this Mellin amplitude M is actually determined by its properties, which are analyticity, crossing symmetry, and supersymmetry, up to a few constants. And 2 of the constants can be fixed at each order using these constraints from integrated form. Using this approach, one can rederive the expression for the scattering amplitude in flat space from the CFT formula. Anyway,
Eisenstein series.
sorry,
Including
including the Eisenstein series. So anyway, this was probably very, very fast, but the takeaway from this is that the same functions of tau and tau bar appear in the derivatives of the S4 partition function and in the flat space scattering amplitude at low orders into derivative expansion. That's the takeaway. So then, how do we see the Eisenstein series from the S4 partition function? So it all relies on this great result by Pestun from 2007, gave the S4 partition function in terms of a matrix model. And for the case of a n=4 superangles theory deformed by an n=2 preserving mass, it takes this following form. G-Mills appears over here. The mass appears over here in these functions M, which are related to Laplace G functions. It's pretty complicated. And then there's some contribution from instantons from the poles of the force sphere. Anyway, it's a finite dimensional integral, so one can imagine evaluating it and expanding it in 1/n. And we did that. It's not an easy calculation, but if we expand it to large n and fixed out, for example, for this particular derivative of the logarithm of the S4 partition function, this is the answer. So there's a first term that goes like n squared. The next term goes like square root of n, and it has this E3 halves. The next term goes like 1/√10, and it has E5 halves. This is interpreted as coming from just tree-level supergravity. This from the Riemann to the 4 interaction. This is from D to the 4, R to the 4. And in this case, there's a precise connection between these coefficients can be matched precisely with the coefficients in flat space scattering amplitude. The reason why these powers of n appear is because the radius of ADS is, by the ADS CFT dictionary, is proportional to the Tuff coupling to the 1/4, which is proportional to n to the 1/4. So that means that if we have a term with k derivatives, that would be suppressed by a power of L to the k, which is n to the minus k over 4. So the Riemann to the 4, for example, has 6 more derivatives than supergravity. So it should be suppressed by n to the minus 6 over 4. And indeed, this is square root of n. It's suppressed relative to n squared by n to the 3. So that's how the counting works.
So in this very strong coupling limit, the instantons matter or not?
The instanton matters. The instantons matter because these E3 halves, E5 halves, the other function will contain all the instanton contributions. That's right. Okay, good. So now I want to talk about the new stuff. So that was the context. And now the new stuff is the following setup. In string theory, let us consider a string or a D1 brain or PQ string that's extended out of the page. And then we have a graviton that comes in and scatters off the string. So in this diagram, time runs up, a vertical direction. The graviton comes and scatters off of the string and goes back. So in this case, there would be a one-to-one scattering process. And again, supersymmetry implies that the scattering amplitude is some coefficient, some prefactor that depends on the polarizations of the graviton or what superpartner of the graviton we're considering times a function of S and T. Where now S and T are analogs of the invariance. They're defined in terms of the momentum of the incoming graviton and the one of the outgoing graviton. So that's on the string theory side. On the field theory side, in the n=4 superangles, we can consider the 2-point function of this operator O, the same that we considered before, in the presence of a half BPS line defect, like a half BPS Wilson line or Tuff line, or a Wilson-Tuft line with ionic charges of P, Q. And in this case too, supersymmetry implies that this 3-point function, 2-point function in the presence of the defect is a prefactor times some function of U and V, where U and V are now ratios of formed by the coordinates of the 2 points of this operator insertions. And of course, there's SL2Z both in string theory and in n=4 superangles that relates amplitudes and correlated with different values for P and Q. particular S duality relates the fundamental string to the D1 brane or the Wilson line to the D2. So now we expect this is the same diagram as before, with different names. So we expect similar connections, but they're more conjectural in this case because many of them have not been shown explicitly. But hopefully, because of that introduction to the context that I provided, it's reasonable to expect that the same functions of tau and tau bar that appear in derivatives of the logarithm of the expectation value of this line operator on S4 is the same functions that appear here. They would also appear in the scattering amplitude at low orders in the derivative expansion. So the computation that we So first, let me tell you a little bit, one slide, what's known about this function f of S and T that appears in the scattering amplitude. So this function over here. In this case, less is known about the effective action. The effective action should start for the D1 brane, for example, with the DBI action for the fundamental string with an Ambigoto action. But then there could be corrections due to the ambient curvature of the space. So the first curvature could be some Riemann tensor squared, curvature squared correction, then d squared r squared, d to the 4r squared. Here r denotes the space-time curvature in 10 dimensions, and d are just derivatives in the tangential direction to the world sheet. But not much is known about what these corrections are. And not much is known about the scattering amplitudes either. For example, for the D1 brane, is just the leading order in G string term that's known. It's again some ratio of gamma functions that has some expansion at low energies, at low values of S and T. But in this case, so this is given by a disk diagram. If we look at the first correction to it, which is an annulus diagram, that's not fully understood because there's a divergence that people don't understand.
Scattering gravitons from outside.
You're scattering gravitons from a D1 brane.
Why would that be included in the dimension of expansion?
Well,
describe scattering the phonons in the string.
No. This R is the coupling to the curvature in 10 dimensions. So as you send in a graviton,
propagation, doing free propagation outside of the brain.
That's right. Okay. So coefficients of these higher derivative corrections are functions of tau and tau bar, but are not modular invariant because it depends. Now the objects that we have, the string and D1 brane are not modular invariants, they're transformed under SL2Z, and they're of course not known. Okay, so what did we actually do? We managed to compute this derivative of the logarithm of the line operator with respect to the mass and set the mass to 0. This has an expansion and 1 over square root of n. These coefficients, and for the case where this line operator is the Wilson loop, the matrix model computation, the modification to the matrix model is very simple. We just add this insertion in it, but then doing the computation and figuring out the large n expansion, that's very hard. We spent many months doing it, but this is the answer. So in the first few orders in at large n, we have only perturbative contributions. And then the first order at which there are some non-perturbative contributions is order 1 over n, where we have 2 perturbative contributions as well as an infinite series of non-perturbative contributions. This expression, at a high level looks similar to the expression for the Eisenstein series, but it's not an Eisenstein series. In fact, it's not even modular invariant. And we also have the expression for the next one, the coefficient of 1 over n to the 3 halves, but I'm not giving it here. It's a little more complicated.
So these functions don't satisfy any kind of differential constraint.
They actually do.
They do.
They do, but I don't know how to prove that. We were able to derive the differential constraint only after knowing the functions. Yeah, they do satisfy differential.
The process could be that there is scattering in the bulk because gravity is nonlinear, and then it comes to the string. How do you separate that from actual scattering from the string?
It has different dependence on tau and tau bar. I'll have a formula.
So which representation?
The Wilson loop in the fundamental representation, simplest thing. That's 5 minutes, okay, great. Good. So now SL2Z relates Wilson loop to a general Wilson Chuft loop. So in particular, one can do an S duality to go from the Wilson loop result to the Topf loop result. And this is the answer here when theta equals 0 for the Topf loop. So again, the first few orders, only perturbative contributions, but then to our surprise, at the next order is order 1 over n. So if we do an S duality transformation on this function, there would be no reason to expect that there's again only a finite number of perturbative contributions and an infinite number of non-perturbative ones, but that's true. It's in this case, it's 4 perturbative terms and then instanton contribution. So in finite number of perturbative terms plus and an infinite number of non-perturbative terms for both the Wilson loop and the Topf. So what is the interpretation in string theory? Well, at each order, this is sort of going to address hopefully this slide and the next Zohar's question. At each order, we have tree-level diagrams as well as loop diagrams that contribute. And here are some examples of diagrams and at which order they contribute. So for example, leading order is just tree-level diagrams. Next order is just loop diagrams. The next order is both loop diagrams and tree-level diagrams. The next order is again both loop and tree-level. So naively, at least, it might seem impossible to distinguish the loop contributions from these contact interactions with higher derivative, these higher derivative contact interactions. But at each order in 1 over root n, the contact and loop diagrams can be distinguished by the tau and tau bar dependence. And I have a conjecture, so I can make a conjecture for the Wilson loop, the case of the Wilson loop. So this means scattering of gravitons off of a long fundamental string in string theory. And the conjecture is the scattering amplitude looks like this. So we call it the scattering amplitude was some prefactor times some function of S and T. And the conjecture is that, so the first term is 1 over ST. This is the tree level contribution. Tree level with just coming from the supergravity and ambiguous action. And then there's a correction proportional to the string length squared. That's a non-analytic function of S and T. This comes from a loop contribution. I don't know what this function is. At the next order, there's again a non-analytic contribution that comes from loop diagrams. I don't know what this is, but it doesn't depend on G string. And then the claim is that there's also a G string square term with some coefficient C1 that's related to the formulas over here. And then at order L string to the 6, there's a couple of non-analytic contributions that come with different powers of G string, either G string to the 0 or G string squared that come from loop diagrams. But there's also a contribution to the scattering amplitude that's proportional to S plus T, and also the function of tau and tau bar that I showed you before. In particular, this function over here. So this is how to distinguish them. At each order, there's non-analytic terms with simpler dependence on G string or on tau and tau bar, and also some analytic terms with more complicated dependence. And those would come from these interactions. We can apply SL to Z to this formula and can get scattering from a function that corresponds to scattering from BQ strings. So in particular, if we do this for the D1 brane, and this IW gets replaced by its S dual, and the S dual had over here had the zeta of 3, and this zeta of 3 sort of matches the zeta of 3. Where did I have it? The zeta of 3 that appears in this expression here of the leading amplitude in small G string. There is a consistency check with the zeta of 3 appears in 2 places. So, anyway, that's sort of what I wanted to say. So we determined, in conclusion, we determined some new functions of tau and tau bar that appear in the effective actions of the order d squared r squared and d to the power squared on extended PQ strings. I did not talk about the actual computations using the matrix model. They're actually pretty involved, but they're in our paper. And for the future, one thing is to make the connections precise between this 2-point function in the presence of the line defect, graviton scattering long string. And also generalized Wilson loops in other representations, not just the fundamental representation, and that would give us access to effective actions on D3 brains with D5 brains. Thank you very much.
You have various special dependence S plus T, right? It's like just polynomial, right? I mean, any interpretation of this?
I don't fully understand where that comes from.
Yeah.
But from the tree level diagrams, one can see that one gets S plus T.
No, this is normal, right? But it clearly plays a special role in your case, right? Because it uses the different function of it.
Right. Yeah, I don't fully understand why it's that. Before Zohar leaves, and maybe we can also thank the organizers. Smita and Zohar and Thomas, who's not here.
I want to say a few words, especially to those who still in the room and endured through the third hardest day. Thank you very much for coming. It was very nice to have you here at Supersymmetry 50. And I hope you return home with new bright ideas about supersymmetry as somebody, where Shlomo mentioned supersymmetry 55, supersymmetry 60. You did. Okay, I'm sorry. And so on. Thank you again.
It's another related to. Yes, if the red is large. Yes.